We're going to continue our guided reading of An Introduction to Analysis by considering the space of of matrices. In particular, we're going to see what happens when you consider linear transformations as objects in and of themselves. By our previous discussion, we've shown that to any linear transformation, you can associate a n by m matrix where t is taken from f to the m to f to the n. But in doing this, you identify the vector space L of f to the m, comma f to the n, of all linear transformations with the vector space of all n by m matrices over the field F. That is, now that we've shown that every linear transformation can be represented as a matrix, we showed that every element in L in the set of linear transformations from Fm to Fn can be associated with a matrix, which you can consider all these matrices as a vector space over as a set of m by n matrices over the field F. This is because this association clearly preserves addition of vectors and scalar multiplications. That is, for any matrix, you can add it to another matrix, and you can scale it. Thus, there's a very natural isomorphism between the set of linear transformations from Fm to Fn and f to the nm. That is, the set of linear transformations is the set of, if you consider transformations as an abstract, and f to the nm you can consider either as a set of square arrays containing n times m elements, or as a single list with nm elements. This is because nm matrices are simply a collection of nm scalars, and therefore we see the dimension of the set of linear transformations from Fn to the Fn is equal to nm. When you do this, you often denote this as f to the n times m, because you want to be clear that n times m is use n times m to denote that you're using matrices, because you sometimes write the side lengths of the matrix. You can say it has size n by m. This might mean you are doing some operations where you need to multiply nm as individual numbers, and then you're taking a set of vectors. This is just clear that you're considering matrices as representations of the set of linear transformations. This stands for the vector space of matrices over the field F having n rows and m columns. That's one way of considering the size of the matrix. If we want to consider some basic facts about elements of f to the n times m, we can consider the zero vector as the zero matrix, which we call big zero. It's a matrix having all entries being zero. And this represents the trivial linear transformation, which maps all vectors in f to the m to the zero vector in f to the n. That is the map that sends all elements to the zero vector in the output space. We'll look at the matrix, which we'll call the identity, in f to the n by n, describes the identity linear transformation f to the n to f to the n. That is the linear transformation that takes the basis vectors delta I to themselves. So clearly this has entries I is equal to delta ij, in the sense that if you consider, because every linear transformation is defined, or every matrix is defined by the linear transformation of the basis vectors, we see the basis vectors are sent to themselves. So you have a 1 there, and they're sent to nothing else, so 0 vectors out everywhere else, which is represented as the delta vector. This is called the identity matrix. It's often convenient to specify the size of the matrix you're using, so you denote the n by n identity matrix as I sub n. For instance, I4 is represented as this identity matrix of size 4. We'll note that you only need one number to specify this, because there is only identity matrices for square matrices, because you can only have the identity transformation from a space to itself. There is no valid identity transformation from a space to another space that is not isomorphic to it in some sense. In particular, if you have a different dimension of it, it cannot be isomorphic. Therefore, you would not have an identity transformation there. If we look back to equation 1.52, which reads as follows, which expresses the coordinates yi in terms of the sum of the matrix entries times the original coordinates of the vector with respect to whatever field you're using, we see that we can view this set of equations, you can view this equation as a collection of linear equations relating the elements, the variables xi and yj. That is, for each yi you would like to find, you have an entire linear equation, and of these you have as many as your transformation demands, namely as many as your as the dimension of your input space, because you can have someone be zero vectors, so the null space is included in that, in the sense that there is sometimes, if you have a non-trivial null space, there will be equations that are all zeros. There will be yj is equal to 0 times x1 plus 0 times ... You can view this system of linear equations as a matrix product. We express the column vector n by 1 of the matrix y vector, and n by 1 matrix generally just means a column vector. You can write this as the product of the n by m matrix A by another column vector, or m by 1 matrix X, which you write like this. And one way of reading this is you take this as a dot product, in the sense that you multiply this column, this entry by this column, this entry by this element, so on and so forth. And if you multiply each of those and then add them together, that sum will equal the first entry of this. And then, for instance, for the third entry, you multiply the first element here times the first element here, plus this element, A32, times x2, and so on and so forth. That will give you all n equations you're going to have to need to solve this. And you write the entry of the, as I mentioned, the y-ith entry in the ith row as the product, the y-ith term in this product is the sum over the index j of the entries aij in row I of the matrix A, and each of the successive entries xj. So you write yi is equal to ai1 times x1 plus ai2 times x2 plus ... up to aim xm. With that, we're going to be able to prove some things in the future. As you'll see, we'll get up to theorem 1.14. But for now, that's where we're going to leave off before we consider a more general form of a product between matrices. Because thus far we've considered very easy matrices, namely column vectors and a single matrix. So next time we're going to consider more complicated products between matrices. Thank you for watching.